Good morning, students. In the last session, we had studied the phenomenon of self-induction. So, we had seen a circuit like this. We had a coil connected to a battery BA and a tap key K. When you press the key K, the current increases from 0 to its maximum value in certain time. If the current increases, then the flux linked with the coil also increases from 0 to its maximum value. Flux increases, the meaning is flux is changing, and whenever there is change in flux, an EMF is induced in the coil. And we had seen that the induced EMF E is given as minus L di upon dt. What are the various terms in this equation? E is the induced EMF, L is a constant called as inductance of the coil, and di upon dt is the rate of change of current. Why there is a negative sign? What does it indicate? The negative sign simply shows that the induced EMF opposes the change in current. So this is an opposing EMF. So it is also called as back EMF. Now, if you want to establish current in the coil, you have to do work against this opposing EMF. And this work done is stored in the coil in the form of magnetic potential energy. And now we are going to derive an expression for the potential energy that is stored in the coil. Now, how to derive an expression for potential energy stored in the coil? So we shall do it in two steps. First, we shall find out how much work is done against the induced EMF to move a small charge dq. What is current? Current is nothing but rate of flow of charge. So you want to have current in the circuit means you have to move the charge in the circuit. So we shall take a small charge dq and find out how much work is done to move a small charge dq against the induced EMF. Now in the second chapter, potential and capacitance, you had seen that the work done to move a charge q under a potential difference V is given as W is equals to Q into V, charge into the voltage. Now here we shall be using this equation to find out how much work is done to move a small charge dq against the induced EMF E. So here V will be replaced by the induced EMF E, and the value of charge q is dq. So we will have dw as E into dq. E is the induced EMF. Let us put the value of the induced EMF, only the magnitude. So we shall get it as L di upon dt. This is the value of E into dq. We shall slightly rearrange the terms. We shall take dt to this side. So you will have L into di dq upon dt. So what is dq upon dt? D by dt of q, rate of flow of charge. What is rate of flow of charge? It is nothing but current. Charge upon time is current. So here you will have this bracketed term as I. Therefore dw is equals to Li di. What is dw? It is the small amount of work done to move a small charge dq against the induced EMF. Now, what is the total work done to increase the current from its 0 to maximum value? Let us say maximum value is I. So we want to find out what is the total work done to increase the current from its initial value 0 to its maximum value I. So total work done will be nothing but integration of dw. So total work done W is integration of dw. What are the limits? Initially the current is 0 and maximum value is I. So integration of dw from 0 to I will give you the total work done to establish a current I in the inductor. Now let us put the value of dw. What is the value of dw? dw is Li di. So I have substituted the value of dw as Li di. Now in this equation, L is a constant. You can take it outside the integration sign. Therefore W will be L integration of I di. Now how to integrate I di? I will tell you one rule for integration. You will be learning integration in detail in maths. Here I will take a reference for integration of I di. Let us take an equation, integration of x dx. X means what? What is the power of x? Is 1. So the rule of integration is whatever is the power of x, you have to add 1 to it. So it will be x raised to 1 plus 1 upon 1 plus 1. What is 1 plus 1? 2. So integration will be what? X square upon 2. Integration of x dx is x square upon 2. Same thing here, integration of I di will be nothing but I square upon 2. So this is the value of the integration. And write the limits. Lower limit is 0 and the upper limit is I. How do you solve the integration now? Put the value of upper limit minus put the value of lower limit. So upper limit is I, so it remains same I square upon 2. Lower limit is 0, so it is minus 0. I takes the value 0, so it is 0. So it is nothing but half Li square. So this is the work done to establish a current I in the circuit. Now just now I told you whatever work is done to set up the current, it is stored in what form? It is stored in the coil in the form of magnetic potential energy. Let us denote the magnetic potential energy as U. So U is nothing but W. And what is the value of W? Half Li square. So U is equals to half Li square is an expression for the energy stored in a current carrying coil or an inductor. So this is a small derivation, but it is important from your exam point of view. This is not a lengthy derivation. It is asked for 3 marks. So I shall revise the derivation once again. So we are deriving an expression for energy stored in an inductor. What are the steps in the derivation? First thing you have to understand, to set up a current in an inductor, you have to do work against the opposing EMF. And this work done is stored in the form of magnetic potential energy. First you have to find out work done to move a small charge dq, and that work done you will get it as Li. Then you find out the total work done to increase the current right from its zero value, initial value, to its maximum value. Let us call it as I. So what is the total work done to increase the current from 0 to I? That you will get by integrating this dw from 0 to I. Then put the value of dw, then solve the integration, and you will get the answer as half Li square. This is the work done to establish a current I in the circuit, and this is stored in the coil in the form of potential energy. So let us denote the potential energy as U. So U, that is the potential energy of the coil, is given as U is equals to half Li square. What is L? L is inductance and I is the current. So this is the magnetic potential energy stored in an inductor. We shall now study a phenomenon of mutual induction. Let us consider a simple circuit like this. We are having two coils, primary P and secondary S, very close to each other. The primary coil is connected in series with the battery BA and a tap key K, whereas the secondary coil is connected to a galvanometer. Now, let us press the key K and then release it and find out what happens. So let us consider the first case when the key K is pressed. What happens when the key K is pressed? Circuit will be closed. Therefore, current through the primary coil increases. Current through primary increases. When the current through the primary coil increases, flux linked with the primary, which is also linked with the secondary, increases. Therefore, flux linked with the secondary coil increases. Increases means what? There is change in flux. And whenever there is change in flux, what is induced in the secondary? An EMF will be induced in the secondary. Therefore, EMF is induced in the secondary coil. This is what happens when the key K is pressed. What will happen when the key is released? If it is released, circuit will be broken. Therefore, current in the primary coil decreases. If the current decreases, then the flux linked with the secondary coil also decreases. Decreases means once again there is change in flux, and whenever there is change in flux, an EMF will be induced in the secondary coil. Therefore, what do you understand by this experiment? So what happens here is EMF is induced in a coil due to change of current in another neighboring coil. So this phenomenon we call it as mutual induction. How do you put it in words? It is a phenomenon in which an EMF is induced in a coil due to change of current in another neighboring coil. This is mutual induction. What we had for self-induction? We did not have two coils there. We had only one single coil, only this circuit was there. So what was self-induction? It was a phenomenon in which an EMF is induced in the coil due to change of current in the same coil, because we had only one coil. But if you have two coils, then it becomes a phenomenon of mutual induction. Now for mutual induction, we shall define a constant. It is called as mutual inductance, or it is also called as coefficient of mutual induction between two coils. We denote it by the letter capital M. So just now we have considered here, when the current through the primary increases, flux linked with the secondary increases. When the current through the primary decreases, flux linked with the secondary also decreases. The meaning is, the magnetic flux linked with the secondary coil is directly proportional to the current through the primary coil. Now current through the primary coil, let us denote it is by the letter IP. And the flux linked with the secondary coil for ns number of turns is ns into phi s. Phi s is the flux linked with one turn of secondary, and total number of turns in the secondary coil is ns. So total flux linked with the secondary coil, it is nothing but ns into phi s. So total flux linked with the secondary coil is directly proportional to current through the primary coil. So let us put a constant in this equation. We call it as capital M. So ns phi s is equals to M into IP. What is M? M is a constant, and it is called as mutual inductance, or it is also called as coefficient of mutual induction between the two coils. Now, whenever there is change in flux, an EMF is induced, and the induced EMF according to Faraday's law is given as E is equals to minus d phi b upon dt. d phi b upon dt stands for rate of change of magnetic flux. Now here flux linked with the secondary is changing. So what is the induced EMF? Instead of phi b, you should put it as ns into phi s. Therefore E is equal to minus d by dt of ns into phi s. So what is ns phi s? ns phi s is equals to MIP. So for ns phi s, I shall write it as MIP. M is a constant. You can take it outside. So you can write like this. E is equals to minus M dIP upon dt. So this is an equation for induced EMF in the secondary coil. Now let us put dIP upon dt, that is rate of change of current through the primary coil, as 1. Then you will get E is equals to M. We shall take only the magnitude, we shall drop out the negative sign. So E is equals to M when dIP upon dt is equals to 1. So let us put it in words. Mutual inductance is the EMF induced in the secondary coil due to unit rate of change of current through the primary coil. So what is the SI unit of mutual inductance? The SI unit, as for self-inductance, it is Henry, and it is denoted as H. So let us put all these units in the SI system. Let us put E is equals to 1 volt. dIP upon dt, rate of change of current, that is 1 ampere per second. So if I put E equals to 1, dIP upon dt equals to 1 ampere per second, then M will be equals to 1 Henry. So when is the mutual inductance said to be 1 Henry? The mutual inductance is said to be 1 Henry if 1 volt of EMF is induced in the secondary coil when the rate of change of current through the primary coil is 1 ampere per second. So this is the SI unit of mutual inductance. So what are the 3 points we have considered today? First, we have defined the phenomenon of mutual induction. Then we have defined what is mutual inductance, and then we have defined the SI unit of mutual inductance. So let us revise the 3 points today. What is mutual induction? It is a phenomenon in which an EMF is induced in a coil due to change of current in another neighboring coil. This phenomenon we call it as mutual induction. What is mutual inductance? Mutual inductance is the EMF induced in the secondary coil due to unit rate of change of current through the primary coil. And when is the mutual inductance said to be 1 Henry? Mutual inductance is said to be 1 Henry if 1 volt of EMF is induced in the secondary coil when the rate of change of current through the primary coil is 1 ampere per second. So these are the 3 points which we have considered for the phenomenon of mutual induction. So this is all for today's session. Thank you.